What if one day the whole world around you started moving in the reverse direction? Water flowed upwards, people walked backwards, and cyclists moved only in reverse gear. You would be confused and bewildered. But as a student of chemistry, you would soon begin to see a resemblance with chemical reactions. Wondering how? Keep thinking. Join me in the studio and we shall find out more about this. Hello and welcome to the show. It is said that winning comes naturally to some, but even then, a minimum amount of motivation is required. Why am I saying this? It's because even in chemistry, spontaneous reactions require a minimum thrust. And in today's episode, we will uncover all this and more. We will see how enthalpy change and entropy are related to spontaneity. We will then familiarize ourselves with the term Gibbs energy change and explore its relationship with enthalpy and equilibrium constant. Finally, in exam Decoded, we will take up all those important exam questions. Energy cannot be created or destroyed. It is converted from one form to another. This is what you have learned as per the first law of thermodynamics. However, it does not tell us about the direction of flow of energy. Like water, heat too flows from a higher level to a lower level and no external energy is required. But if you want water to flow in the reverse direction, it will require an external agent like pressure in the case of a fountain. In case it is still a bit unclear, let me give you another example. When a golfer hits a ball with a club, it reaches a maximum height and then falls on the ground. While force was required to lift the ball in the air, there wasn't any external force required to bring it down. The process is spontaneous due to gravity and does not require any external force or energy on the part of the golfer. Another aspect of a spontaneous process is that it has a natural inclination to move in a particular direction. Let me demonstrate this using a drop of ink. When I put this drop of ink into this beaker full of water, the drop starts to dissolve. It spreads automatically without the involvement of any external agency. This reaction takes place in only one direction and is thus a spontaneous reaction going towards a minimum energy state, which in this case is obtained by the dispersing of ink drop all over the water surface. From all the examples that we have seen, we can say that any process that has a natural tendency of occurrence in a particular direction and is reversible only by application of some external agency is known as a spontaneous process. The question that now arises is that how can we determine whether a chemical process is spontaneous or not? And the condition is that we should not have to carry out the process to determine that. One of the criterion used to classify reactions is reaction enthalpy delta H. In chemical reactions, heat energy changes are measured as heat content called enthalpy. As you are aware, heat flows spontaneously from hot to cold, that is, a system will lose energy easily. As a result, we can even say that exothermic reactions are spontaneous. In other words, a reaction which has delta H negative is spontaneous. Now what about endothermic reactions? Can they be spontaneous also? If you think they cannot, then let me give you an example. Take 5 milliliter of water in a test tube and measure the temperature. Now add 1 gram of ammonium chloride to this. It will dissolve easily. If you note the temperature of the solution right now, you will note a decrease in the temperature. As you are aware, solubility of ammonium chloride in water at room temperature is an example of an spontaneous process. And the decrease in temperature that you saw proves that it is also an endothermic process. In other words, a reaction which has delta H positive can also be spontaneous. In conclusion, we can state that not only exothermic reactions but also endothermic reactions can be spontaneous. And the reaction enthalpy is not an adequate indicator of spontaneity. In the late 1850s, Rudolf Clausius introduced the scientific world to a new term, entropy. Let us look at this pile of coins placed on this table. It is quite orderly. After picking up the pile, if I drop the coins back even one by one, I will never be able to get the formation of the pile as orderly as before. Let's see. Now, why do you think these coins did not pile up again in the same ordered fashion? This randomness of piling is a measure of entropy. It is denoted by the letter S. You must note that more the value of S, the more is the randomness. Amongst the three states of matter, solids have the most orderly molecular arrangement, and this orderliness decreases as one goes from liquids to gases. So we can say that entropy increases from solids to liquids to gases. But how do we measure entropy? The change in entropy delta S can be calculated as the difference between entropy of the final state and that of the initial state. Delta S is equal to heat absorbed or evolved divided by the temperature at which the change takes place. Now, delta S is a key concept in understanding the spontaneity of a process. But before I tell you how, you must answer a question for me. Which of the reactions is associated with the more change in entropy? First, N2 plus 3H2 gives 2NH3. Second, CO plus 2H2 gives CH3OH. While you think of the answer, I will take a short break. And when I come back, we shall resume our discussion on delta S and even compare answers. So don't go anywhere. Welcome back. Before the break, I had asked you a question. Which of the following reaction is associated with more change in entropy? First, N2 plus 3H2 gives rise to 2NH3. Second, CO plus 2H2 gives rise to CH3OH. The answer is, in the first reaction, gaseous reactants are changing into gaseous products, while in the second reaction, two gaseous reactants are changing into a liquid product. Clearly, second reaction shows more negative change in entropy, as entropy of a liquid is less than the entropy of a gas. The right answer therefore is second reaction. Let us now resume our discussion on the randomness in a system. The randomness in a system increases on supplying heat because of the increase in the kinetic energy of the molecule. Thus, entropy is directly related to the heat added to the system. In the context of entropy, the second law of thermodynamics becomes relevant because it states that the entropy of the universe always increases during a spontaneous change. I suppose we can make this point clearer by considering the example of the system of oxidation of iron. In this reaction, the entropy change is minus 549.4 joules per mole per Kelvin, and the enthalpy change is negative, that is minus 1648 kilojoules per mole to be precise. Now you know that negative enthalpy means that the reaction is exothermic, and so the reaction should be spontaneous. However, since the entropy change is negative, the reaction should be non-spontaneous. That is quite perplexing contradiction to be faced with, isn't it? But there is an explanation for every phenomenon. You just need to keep thinking while solving. The reason we are faced with this seeming contradiction is that we have seen the entropy of the system in isolation and have not considered the surroundings. This is a very important point, and often students get confused in exam questions because they forget it. So pay attention. Whenever we talk about entropy, we must consider the entropy of the whole universe. From the value delta H is equal to minus 1648 kilojoules per mole for the system, we can conclude that delta H for the surrounding is plus 1648 kilojoules per mole, because heat released by a system is equal to heat absorbed by its surroundings. On using this value of delta H for surroundings, we will get the value of delta S equal to 5530 joules per mole per Kelvin for the surroundings. As a result, the total entropy change, which is a sum of delta S for the system and delta S for the surroundings, becomes positive. That is, entropy increases, making the overall process spontaneous. Logical, wasn't that? Far from the contradictory process that it seems. But then, that is the beauty of chemistry. It demystifies all sorts of paradoxes. As you have seen, neither decrease in enthalpy nor increase in entropy can individually predict spontaneity of a reaction. Also, since most chemical reactions occur in open or closed systems, to predict the spontaneity of a reaction, a new thermodynamic function called Gibbs function or Gibbs free energy is used. This is a combination of both enthalpy and entropy. Gibbs energy, or G, is the difference between enthalpy and product of temperature and entropy. Change in Gibbs energy at constant temperature is given by the equation delta G is equal to delta H minus T delta S. Now let us see the significance of delta G by relating it to spontaneity. For this, you must recall that heat released by a system is equal to heat absorbed by its surroundings. Now, delta S system is equal to delta H system by T. Therefore, delta S surrounding will be equal to minus delta H system by T. Now, delta S total will be equal to delta S system plus delta S surrounding given by equation 2. At this point, we will now replace delta S of system with delta H system divided by T given by equation 3. Delta S surrounding is given by equation 4. Changing the terms in equation 2 in terms of system, because most of the chemical reactions occur in open or closed system, we get equation 5. On rearranging, we will get T delta S total is equal to T delta S system minus delta H system given by equation 6. You might be wondering as to how you will be able to deduce the spontaneity of a reaction using the values of delta G. Here is the answer. If delta G is less than 0, the process is spontaneous. If delta G is equal to 0, the process is in equilibrium, and if delta G is greater than 0, the process is non-spontaneous. It's time now for me to reveal the link between the reversed world that you saw at the beginning of the show and chemistry. But before I do that, you must know the relation between the equilibrium constant K and Gibbs function. Mathematically, the relation is denoted by delta G reaction is equal to delta G naught reaction plus gas constant R times temperature T in Kelvin, natural log of K, where delta G naught is Gibbs energy for a reaction in which reactants and products are in standard states. Since at equilibrium delta G is 0, we get delta G naught reaction is equal to minus RT natural log of K. If value of K is greater than 1, then the reaction proceeds in forward direction, that is, it is product making, and delta G is less than 0. If value of K is less than 1, then the reaction proceeds in the backward direction favoring the reactants, and delta G is greater than 0, which means that it is non-spontaneous. So what is non-spontaneous in chemistry is also non-spontaneous in life. It is, however, both natural and spontaneous for you to have doubts, just like my young friend here.
I find calculation of delta G very confusing. Can you please tell me how to do it?
That's a step in the right direction, knowing your weakness and resolving it. To answer this question, let us look at a probable exam question. The equilibrium constant for a reaction is 10 at 300 Kelvin. So what will be the value of delta G for the reaction? To solve this, we will make use of the formula delta G is equal to minus RT ln K, which we have just discussed. Recalling this equation is the key to solving such questions. You also know that gas constant R is equal to 8.314 joules per mole per Kelvin, and the temperature T is given as 300 Kelvin. On substituting the values, you will get delta G is equal to minus 5744.14 joules per mole. After this, I hope such questions will not confuse you anymore. It's time for a short break now, but stay tuned because up next is Exam Decoded. Welcome back. Today we have learnt about the spontaneity of chemical reactions. And the key points of today's session are, for a spontaneous process, neither the decrease in enthalpy nor the increase in entropy alone can help in predicting the spontaneity of a reaction. As a result, the concept of Gibbs energy function is used to predict the spontaneity of a reaction given by G is equal to H minus T into S. The relation between Gibbs energy change and equilibrium constant is given by delta G naught for the reaction is equal to the negative of the product of the gas constant R, temperature T, natural log of equilibrium constant K. With that recap, I think you are headed in the right direction, which is to meet the challenge of Exam Decoded. Welcome to Exam Decoded, the surest formula to get top scores. We will start with the rapid fire section, where I will ask you 5 questions and you will get 5 seconds for each question to answer. Each question carries 1 mark. Remember to keep a tab on your scores because we will compare the scores in the end. So all fired up for the rapid fire? Okay, here is your first question. What is the SI unit for Gibbs free energy change? A. Kelvin, B. Joules per mole, C. Pascal, D. Newton. And the right answer is B. Here is the next question. Entropy of the system is denoted by what symbol? And your options are A, H, B, J, C, S, D, G. This one is much easier than the last one. The right answer is option C, that is S. Next question. For exothermic reactions, delta H is negative. Is this statement true or false? If your answer is false, then you are obviously wrong. It is true. For exothermic reactions, delta H is negative. Here is your fourth question. For a spontaneous process, delta G is greater than 0. Is this statement true or false? If you have been watching the episode closely, I am sure you have already worked out the answer by now. The correct answer is false. And here is your final question. Relation between Gibbs energy and equilibrium constant is given by delta G naught of the reaction is equal to the product of gas constant R, temperature T, natural log of equilibrium constant K. True or false? The right answer is false. Time for us to compare the scores. If you got all the answers right, congrats. You are a high flyer. Keep up the good work. If you scored 4 or 3, then you are an achiever. Anything less than 3 makes you a learner. But with a little more practice and guidance on www.topperlearning.com, you will soon be back on track. The topic Entropy and Gibbs free energy belongs to the unit Thermodynamics and carries a weightage of 6 marks. So according to our weightage meter, it is critical for your exams. Probable questions from topic Entropy and Gibbs free energy can be short answer type for 2 marks and long answer type for 3 marks. And these questions can pertain to your conceptual ability and numerical ability. Let's solve a probable numerical ability exam question for 3 marks. Predict whether the following reaction is still spontaneous at 427 degrees centigrade. Given that delta H is equal to 92,000 joules per mole and delta S is equal to minus 200 joules per Kelvin per mole for the reaction. N2 gas plus 3H2 gas is in equilibrium with 2NH3 gas. Now since free energy change for a reaction is given by equation delta G is equal to delta H minus T delta S, we write that as the first step. This will fetch you half a mark. You must now convert the given temperature into Kelvin by adding 273. This conversion will get you another half mark. On substituting the values of entropy change and enthalpy change from the values that you are given in the question and calculating, you will get delta G as 232 kilojoules per mole. This calculation is worth half a mark. Now, since delta G is positive, you can easily infer that the reaction is non-spontaneous. This is your final answer and will fetch you 1 mark. I hope that you have noted the stepwise approach to the answer, because if this kind of question comes in your exams, I want you to get nothing less than full marks. It is time now to go over to an exam expert who has some invaluable tips to help you crack your exams.
In the topic Entropy and Gibbs free energy, while preparing for your exams, students, you should know that entropy is measure of randomness or disorder of a system. It is an extensive property and is a state function. In an isolated system, spontaneity of a process is decided by entropy change. Another thermodynamic function, that is delta G, Gibbs free energy change. Delta G, that is Gibbs free energy change, enthalpy change and entropy change are related by the expression delta G is equal to delta H minus T delta S. Students, you should also remember the relationship between delta G and equilibrium constant. I am sure keeping these points in your mind, you can score well in your exams.
If you keep all these tips in mind and maintain your focus, you will surely get great scores. Remember, it is not about how hard you prepare, but how strong your fundamentals are. So get your basics right and you will head spontaneously in the right direction. That leads to top scores. See you next time.